Hello, this is part D of the Chapter 8 lesson. In previous parts we've been talking about things like the type 1 error, type 2 error, and power of a hypothesis test. In this section we're going to put it all together and talk about how we can calculate the necessary sample size for doing a hypothesis test. So to illustrate this, let's look at example 8.10 from the textbook. And in this example, it says that the mean fasting blood glucose level in people free of diabetes is 95 milligrams per deciliter with a standard deviation of 9.8. Now, where this population mean of 95 and standard deviation of 9.8 come from isn't terribly important. What we want to do in this example is consider the population of people who drink at least 2 cups of coffee a day. So this is a different population of people than up here. Up here we have a population of people free of diabetes. Down here we have a population that have drink at least 2 cups of coffee a day. Now a researcher claims that the mean glucose level of this population is different than 95. So essentially what this researcher wants to do is compare this population down here to this population up here. And he's claiming that this population is different from this population. So the mean of the second population is different than 95. So we're going to test this claim with the hypothesis test. So the parameter of interest here in this test is mu, the mean glucose level of all people who drink at least 2 cups of coffee a day. So we're making a claim about the mean of this population down here. Now the claim is that mu is not equal to 95. And so our hypotheses are going to be the statements that mu equals 95 for the null, and the alternative is that mu is not equal to 95. And we're going to use a 0.05 significance level to test this claim. So let's make an observation here about these hypotheses. If the population mean really is different than 95, then the null hypothesis is a false statement and we would want to reject it. So the null hypothesis is the statement that mu equals 95. Well, if mu were different than 95, then the null hypothesis would be a false statement and we want to reject it. Well, the likelihood or the probability of rejecting a false null hypothesis is what we call the power. So the power of the test is the likelihood that the test will detect this difference. Here the difference we're talking about is the difference between the population mean and this value of 95. And so the researcher believes that a difference of 5 milligrams per deciliter is practically significant. And so the question that we want to answer here is what sample size is necessary so that the test will have 80% power to detect a 5 milligram per deciliter difference. So we haven't done the sampling yet. We haven't collected our data yet. We want to determine what sample size is necessary so that we're going to have 80% power to detect this 5 milligram per deciliter difference. And the formulas here are rather complicated. They're given by these somewhat nasty looking formulas here. So let's talk about what these formulas mean. Important thing here is we've got this quantity ES, which stands for the effect size. The effect size is the absolute value of this difference divided by sigma. This difference here is what we call the clinically meaningful or practically important difference in the means. In this case, this meaningful difference is 5. Now this number in the denominator is sigma, an estimate of the population standard deviation. So we're going to take this difference, divide it by sigma, and we're going to get this effect size. And then we're going to take this effect size and put it in the denominator over here, and the numerator are these quantities which are critical z-values, and these numbers in the subscripts alpha, that's my desired significance level, which is typically 0.05 or a 95% confidence level, and then beta, or 1 minus beta, that's the power. And so at the typical 95% confidence level and 80% power, these critical values are 1.96 and 0.84. So I'm going to plug those numbers in there, divide it by the effect size, square it, and that's going to give us the necessary sample size. Okay. So if we start plugging things in here, the meaningful difference or practically significant difference is 5. That's the difference that we'd want to be able to detect. And then an estimate of our population standard deviation is the standard deviation from that first population given in the example, which was the population of people free of diabetes, 9.8. And so now we're going to plug things into our formula. Here's the effect size. We take our difference divided by 9.8. We get 0.51. And then we're going to plug that number into our formula for n. These critical values are 1.96 and 0.84. Divide that by 0.5. Do that arithmetic, square it, and we get 31, or 30.1. And so we're going to round that sample size up. And so that tells us that we're going to need a sample of at least 31. So in the end, these formulas, these calculations were fairly simple, but understanding what's going on behind the scenes is rather complicated and what all these things mean. So in the end, what we do is we take our meaningful difference, divide it by an estimate of sigma, and then we add these two numbers together, divide it by that effect size, we square it, and we're all done. So let's look at one last example here. This is example 8.1 from the textbook. So in 2002, the Americans paid an average of $3,302 per year on health care and prescription drugs. I think we've looked at this scenario before. Now, an investigator claims that in the year 2005, average expenditures are different. And so to test that claim, we went out and we got some data from people in the year 2005. We surveyed 100 people. We calculated a mean cost of $3,190, and we got a standard deviation of $890. And so we're going to use this data to test our claim. So the parameter that we're making a claim about is mu, the mean healthcare and prescription drug costs of all Americans in the year 2005. So if we set up our hypotheses, the claim is that mu is different than 3,302. So that's the alternative hypothesis. The null is the statement that mu equals 3,302. And so now to test our claim, we're going to use the workbook chapter 7 and the worksheet mean, which we used back in chapter 7. We haven't used it here in chapter 8, but we're just going to use this for illustrative purposes. And so we enter our numbers here. Here's the number of the null hypothesis. Here's the sample mean, sample standard deviation, the sample size. This is a two-tailed test because we have a not equal to sign in the alternative hypothesis. Here's the test statistic. Here's the p-value, which is 0.2. Now we interpret that p-value by comparing it to the significance level, 0.05. In this case, the p-value is much greater than 0.05. And so we do not reject the null hypothesis. And so that means that the data do not support the claim, and we would interpret that by saying there does not appear to be a significant difference in the average expenditures between the year 2002 and 2005. So we thought maybe there was a difference, but our data indicates that there just isn't that much difference for us to conclude that there is a difference. So now the researcher says, well, wait a minute, let's take a step back. Maybe there is a difference, but the test wasn't powerful enough to detect that difference. So in other words, the researcher is thinking that maybe a sample size of 100 was not large enough. So the researcher wants to go out and collect more data to try to do another hypothesis test, and maybe they will be able to detect that difference in this new hypothesis test. And so in order to determine what sample size we need to determine a meaningful difference. So this researcher believes that a difference of $150 is meaningful. And so the question that we want to ask now is, how large does the sample size need to be so that the test has 80% power to detect a $150 difference? Okay. And so, in other words, this meaningful difference is 150. Sigma, our estimate of the population standard deviation, is, let's use the standard deviation from the previous survey, which is 890. Okay. And so now we'll calculate our effect size. We'll take our meaningful difference, divide it by the standard deviation. We get 0.17. Now we calculate our sample size, where we take our critical values, divide it by this effect size, square it, and that gives us a sample size of about 272. So we need a sample of at least 272 to detect this $150 difference. So what that means is that our original sample of size 100 was underpowered to detect a difference of $150. So this kind of confirms the researcher's suspicion that maybe there was a difference in this population of people in 2005, but the test just wasn't powerful enough to detect it. And so in order to detect this difference with 80% power, we would need a sample size of at least 272. So to kind of summarize these calculations and these past few lessons, determining the necessary sample size is important, and as we've seen, it's very complicated. There's lots of different issues involved here. There's the power, which we can think of as the likelihood of detecting a difference. There's the significance level, which is the likelihood of committing a type 1 error. And so we want a high power and a low significance level, right? We want to be able to detect a difference, but we don't want to commit a type 1 error. So we want a high power and a low significance level. And as our calculations illustrate, we can do this by selecting a large enough sample size and a small enough significance level. So kind of this is the key result here. In order to get really good results from our hypothesis test, we need a large enough sample size.